Okay, so we move on now to study the unit impulse function or the delta function. I want to encourage you to actually look at the notes because I give you more details on how this function is defined and also a proof of the main formula, which is the Laplace transform of it. I'm going to focus here just on a brief discussion on what it means, and then some discussion about the notation and the way you take the Laplace transform. So roughly speaking, what you want to describe is a rate-like quantity that occurs over a short period of time. So a rate-like quantity, like any rate, for example, you can think about a velocity, a density-like function, right? I mean, something that in order to see its cumulative effect over an interval, you have to take the integral of it. So for example, if I have a velocity, which is a rate-like quantity, right? I mean, the velocity is the, what is it? It's the rate of change, right, of the displacement. So if I integrate a velocity, I get the displacement, right? I mean, I get a displacement over a certain interval of time. So in the same manner, if you integrate any rate-like quantity in an interval of time, you will see the output of that quantity cumulatively over that interval of time. Now, what you want here is basically that rate-like quantity to occur in a short burst, like in an instant, a short period of time, basically of length 0, right, focus on a specific time point in the axis. So, for example, like a surge of current, like a jolt or a lightning, if you want. Let's say you want to model this lightning, at times a, you want essentially that rate-like quantity to be described on an interval of length essentially 0 around the point A. So like with anything in calculus, this is a limiting process basically. So to formalize this type of mathematical tool, if you want, you can start with, like I said, the limiting process. So you can start with a time point A in a small interval near A, let's say from A to A plus H. So you have an interval of length H near the point times equals A. So you imagine a function which is actually 0 outside of this interval. So outside A of A plus H, the function is completely 0. And between A and A plus H, you want the integral of that function, the output, if you want, of that rate-like quantity, to have a specific value. And again, for standardization purposes, you want that value to be 1, because you can always change it by multiplying with a different constant later. So the easiest thing is to imagine that in the interval of length h, the function value is 1 over h, because when you take the integral, that's just the area of that rectangle, so that's going to be 1. So h times 1 over h is 1. So this will be essentially an output equal to 1 over an interval of length h. What you want to do after that is to do a limiting process. You want to shrink h to 0 while keeping the area of this rectangle equal to 1. So I mean, I want this value 1 over h to be maintained, but notice that as you shrink h, 1 over h increases. And as h goes to 0, 1 over h jumps to infinity. But you want this jump to be controlled essentially, right? So that at all points, at all times, the area of the rectangle is always 1. So there is no classical function for this because, you can say the function returns infinity. 1 over 0 as a limit is infinity, and you cannot take an integral of infinity, right? So this is really a formal notation. Think of it as, I should even put it in the quotation marks, because for lack of a better notation, basically, just to make an analogy with the classical integral, basically this is a description of this limiting process. So for all practical purposes, think of delta function as doing nothing for the entire timeline except at times equals a when it returns in the form of an integral, if you want, the value 1. So it returns that the cumulative effect is 1 when t equals a. It does nothing for the other time value in the axis. So the proof of so even though this delta function is not a function in the classical sense, you can show that if you take the Laplace transform of these limiting functions, the Laplace transform actually has a nice format. It's given by e to the minus as, which is again really the nicest part of this whole thing. Although this is not a classical function, the Laplace of it is a classical function, even a nice one if you want, e to the minus as. So these types of problems, when you involve the delta function, really can be handled nicely with the Laplace transform. Look at the notes to see the proof of this formula. And I put these two formulas together just to make sure you don't get confused, right? I mean, the Laplace of the step function, which means something completely different, is given by e to the minus as over s. The Laplace of the delta function, or the unit impulse function, is e to the minus as. So there is no over s on the bottom. And again, for reference, I wrote here the delay theorem so we could use it later. So all of these are in the formula sheet in the Laplace table. At this point, we should just go over and solve a couple of examples with involving the delta function. Well, let's do a basic one in the beginning, right? So I mean, let's say I want to find the Laplace of delta t minus 3 plus 7 step of t minus 5. So basically, it's like a burst of magnitude 1 at times equal 3. Nothing happens before and after that until when t equals 5, when the function returns 7 and it stays 7 forever. So the Laplace of this, again using the linearity property, is just e to the minus 3s, applying this formula, and then the second term, e to the minus 5s over s. That's just a basic warm-up if you want, and now let's actually deal with some ODEs, some differential equations involving the delta function. So let's start with a simple first order ODE. Let's say y prime equals 7 delta of t minus 1 minus 5 delta of t minus 3, and then in the beginning y of 0 equals 5. Equals 6. All right. So how do we solve it? Like with any other ODE, via Laplace, take the Laplace on both sides. So on the left we have s times big Y minus y of 0, which is 6. This is 7 e to the minus s minus 5 e to the minus 3s. Okay, add 6, divide by s, and y is going to be 6 over s plus 7 over s squared e to the minus s minus 5 over s squared e to the minus 3s. So notice that you still end up with the delay theorem. That the big Y is very similar if you look it up, whether you have a step function into the ODE or a delta function. When you're done, you still have this exponential that's typically multiplied by that's over s. I'm sorry, not squared. I was thinking about the previous example, but so 6 over s, 7 over s minus 5 over s. Yeah, so this one actually doesn't require the delay theorem because it's just over s. So when you take the inverse Laplace, that's just an application of the table. This goes into 6 inverse of 1 over s. E to the minus s over s goes into the step function, so that's 7 step t minus 1, and then minus 5 e to the minus 3s over s step t minus 5. Yeah, so my next example will be with the delay theorem. Right, so this one didn't require the delay theorem because you just ended up with a direct application of this. I was thinking about s squared because if this was a step function, you had an over s already to begin with. So with the extra over s, then you had over s squared, like in the previous example. So let's do one that actually does require the delay theorem. So let's say y double prime plus 4y equals the delta of t minus 3, y of 0 equals 1, and then y prime of 0 equals 0. Okay, so let's carefully apply the Laplace on the left side. S squared big Y minus s times y of 0, which is 1, minus y prime of 0, which is 0. Then plus 4 big Y equals e to the minus 3s. And that's it, not over s, right? Because that's the delta function. Move s over and pull out y. So y s squared plus 4 s plus e to the minus 3s. And divide by s squared plus 4. And you get that. Remember what I told you before, it's very important not to combine these, because it's very tempting to combine them. Because you have on the top s plus this over s squared plus 4, but that doesn't help. Taking the inverse Laplace requires two different techniques. Delay theorem for this. This is just the table. Okay, so when you take the inverse Laplace of that, let's write it here. Little y would be cosine of 2t. That's just the direct application of the table. Here it goes with sine. I need the 2 over 2 to produce that sine. And remember the delay theorem. How do you do it? Take the inverse Laplace of this, which is sine of 2t, but make the substitution. So it's going to be sine of 2 quantity t minus 3 step t minus 3. Okay, so again, take some time if you want to go over slowly on this one, right? So I mean, inverse Laplace of this is sine of 2½ sine of 2t. Don't forget to replace t with t minus 3, because that's what the delay theorem states. And again, the solution makes sense. Let's think in terms of the mass spring system. As I said before, this is like an undamped mass spring system. It has an initial displacement and a zero velocity, but in the beginning the spring is stretched. You let it loose until t equals 3, nothing happens. So what does an undamped oscillator do? It'll oscillate with the frequency given by the characteristic roots, which are plus minus 2i here. So this is essentially what happens with the spring system, going back and forth until the jolt at times equal 3, the impulse, the unit impulse, happens at times equal 3. When that happens, the motion will change in response to that impulse, and it will stay there forever because there's no damping to dissipate that effect. There's no damping, so the motion takes on forever, but the type of motion changes when t equals 3. So let's go over one last example. So that'll be, I think we can fit it here. That'll be example number 4, which is a very similar one. I want to point out on a similar example in the book, so that you don't get confused with the answer, because they simplify the answer in a way that it may not be obvious. So it's actually very similar to the previous one. Very, very similar. Let's change though, make a little bit of a change in the initial condition. So let's say y of 0 equals 0 this time. So unlike the previous example, we have 0 displacement, but the initial velocity is 1. So we still have some movement in the beginning. The time value where the change happens is t equals pi. So just like before, when we apply the Laplace, on the left we have s squared big Y minus s times y of 0, which is 0. Notice the difference, right? So, and then minus y prime of 0, which is 1, plus 4 big Y, and on the right hand side, of course, e to the minus pi s. Solve for y, plug, pull out s squared plus 4, move 1 on the right, and then finally big Y is 1 over s squared plus 4 plus 1 over s squared plus 4 e to the minus pi s. In anticipation for the fact that this goes back to sine, again in both cases you're going to need to put that 2 on the top and multiply by 1/2. Again, if at this point, when you go over this, if you are at this stage in the course, if it's still not clear to you quickly why I put this 2 times over 2. Take a moment and review what we did in the beginning of the chapter when we went over some of these examples. Again, the idea is to match it with the formula sheet. You should have that table of Laplace formulas in front of you until it becomes automatic. The reason you need to do these little changes in order to make the function here fit the fit what you have in the table, right? So yeah, so times 2 over 2. This looks like an I'm sorry. So let's put it like that. Let's just, it was 1 over a square plus 4 times 2 over 2. I put another 1 over 2 and look like 11. So inverse Laplace, right? So how do I, let's write it here. Inverse Laplace of the first part is going to be 1/2 sine of 2t. Inverse Laplace of this is going to be 1/2 sine of 2t, but don't forget the time shift. So instead of t, you're going to put t minus pi, and then multiply that part with step t minus pi. Okay? Remember what you did here. Inverse of this, and then replace t with t minus a before you write it on the left side of the step function. Okay? Because you had the same function here, both went back to sine of 2t, but this one needed the time shift because of the delay theorem. What you're going to see in the back of the book, let me write it here, for problems like this, is that they write the answer 1/2 sine of 2t. If I can fit it here, maybe I'll write it here. So they will write it like that, 1/2 sine of 2t plus 1/2 sine of 2t again, which is very confusing, and I sympathize with you if it is, which is the reason I want to take some time to explain it. So all of a sudden, so I drill into your head that you need to do this time shift, and all of a sudden they revert back on that step function with from sine of 2t minus pi with sine of 2t. Now the reason you could do this is because sine is periodic with period 2 pi. Does that make sense? So I mean, when you write sine of, when you have here sine of 2t minus 2 pi, right, if you distribute that too, you could remember now that sine happens to be periodic with period 2 pi. So if you add and subtract multiple of 2 pi's, that doesn't affect the value of the function. But this is simply because I chose pi here for the time value. If I chose any other number like 3, 4, 5, whatever, you couldn't do this simplification. So the magic reason why minus pi disappears is simply because sine is periodic with period 2 pi. Don't worry about this too much, because if you don't do this in the test, and if you leave the answer like that, I don't care. That's just as correct. So that's not an issue. But there is a similar problem in the book like this, and that's the reason why I want to mention, because you will write it correctly, and then you will wonder why actually it disappears after that, unlike in previous problems like this one, for instance. So hopefully at this point you are at the end of 2 days, because if you do this, if you try to do this in one setting, it's not going to work. You really have to take your time on this section, otherwise you'll get frustrated if you don't allow enough time to practice. So we're going to have one more section on this on the Laplace transform when we learn an nice operation on functions that has a very nice property via Laplace transform. So that allows you to write in a very elegant way and compact way the solution of any linear ODE. So I'll see you next time.